Have to wait for the signal there. So good afternoon, and thank you for joining us for our CGD seminar this week. I have the pleasure of introducing John Fasullo as our speaker today, and John will be speaking on Rethinking Wildfire's Climatic Role. Just a little bit about John. He's a project scientist in CGD, and he's also a research associate in the Atmospheric and Oceanic Sciences Department at CU. He has a Bachelor of Science degree in Applied and Engineering Physics from Cornell, and a Master's of Science and a PhD in Astrophysical, Planetary, and Atmospheric Science from, again, CU. John's research focuses on societally relevant topics aimed at understanding climate variability and change, improving climate models, and supporting the climate science community. Just two recent examples of his research include the emergence of the pattern of sea level rise driven by human activities and the dependence of strategic solar climate intervention on the background scenarios in model physics. As in our past seminars, we'll take questions from the in-person and online audience at the end of John's talk. So if you're joining us virtually, please use the Slido link to input any questions you may have. You can find the link on the YouTube page or by going to slido.com and looking up CGD seminar. So take it away, John.
All right. Thank you, Betty. So as you might be able to tell from the title of my talk, the focus here is not going to be on any single publication, but on actually about a dozen publications that we've done over the past few years. And the goal is to illustrate this somewhat surprising influence of biomass emissions in CESM2 on climate. And so a lot of things that we went into these studies thinking ended up not to be true. And we really saw the surprisingly large effect of biomass emissions on the climate state. And in fact, that is what I mean by rethinking wildfire's climate role. I'll illustrate a few points as to how we currently think of it as a very secondary forcing, not very important. We don't really have to get it that correct. But in fact, we do have to get these things correct. And it's not easy to do so. There's reasons why we've kind of been sloppy with them in the past. And I think this really points to the expertise within CGD and the opportunities that exist for improving both climate predictions and climate projections. Let me also note that I'll mention a lot of authors during the course of the talk, but particularly Nan and Rebecca have been really constant contributors to all the work that I'll talk about, and so I wanted to acknowledge them here. I was asked to say a few things about my research interests. The probably most influential collaborator of mine was Kevin Trenberth. The first decade I spent here, he and I published several dozen papers on the energy budget, on the flows of energy through the system. And really, that's the common theme that ties together what might seem to be a hodgepodge of different topics. As Betty said, I work in geoengineering, I work in climate variability and sea level. But obviously, with the Earth's energy imbalance, you get a certain amount stored in the ocean, and that gives you change in ocean heat content and also in sea level. And so the connection there is clear. With Jerry Meal, we did a paper over a decade ago now, looking at decade-to-decade fluctuations in Earth's surface temperature. And it turned out that ocean heat content was actually critical for explaining those variations. And then Clara Desser's been very instrumental as well, very influential with her work on large ensembles, but also modes of variability. And so really the expertise within NCAR has been fundamental to my work, and I'm very thankful for it. Basic motivation, I'll start out by talking about some of the observed changes in fire in a warming climate, the various expectations that we would see this. We certainly see it going on now. And then this really unique, what I'm calling topic one here, is the Australian wildfires of 2019-2020 and their impact on climate, which is one of the things I was alluding to before about unexpected, very large unexpected response in the climate system, at least in CSM2, and I'll talk about the caveats a bit later. This topic one relates to prediction and climate prediction, and so the Australian wildfires were a key part of that. And at CGD, we have the SMILE ensemble that Steve Yeager has led, and we designed a specific iteration of the SMILE ensemble to quantify and understand the effects of the wildfire smoke on the climate system. Topic two relates instead to how biomass emissions are handled in CMIP6 and some of the details in the CMIP-6 forcing that led to some unexpected effects in the CMIP simulations. I'll talk about them. This was a paper published in GRL, and there were a number of interesting follow-ons, some by people in this room, and I'll mention them. And then lastly, I'll touch on what I see as these opportunities for CGD to really push the science forward. I don't think anyone else is actually doing this science, and maybe we're one of the few labs that can. And so I'll try to touch on those topics. Just to give you a sense for context, obviously we've had a number of fires. Kind of Colorado's been in the front row of seeing the changes in wildfire around the country. We've had the Marshall Fire on the top left here. That's a picture taken from NCAR on the day it occurred. Had like 80-mile-an-hour winds. You can see the winds kind of blowing the smoke, and very important feedback onto the fire itself. The circulation in the atmosphere, those clouds are all part of the overturning circulation that occurred during that event. But you go back to 2020, and we actually had 4 of the largest wildfires in state history in 2020. And so, obviously there seems to be some sort of a trend, and we don't have any real questions as to what's driving that. If you went to Fort Collins in 2020, you see the picture down here. That's during the Cameron Peak Fire. And so there's massive fire just to the west of Fort Collins. That smoke is advected right across the city, and there were parts of the city that you couldn't see a block or two down the road during this event. So huge event. But I like the picture of the video on the upper right here. This is California in 2021, because it gives you an idea of actually the fires that we're going to be talking about in this talk. We're not talking about the individual fires that you can see here, but rather these fire complexes. So areas burned on the order of 1 million acres. So large wildfires, much bigger than even some of the ones we saw in Colorado. And these are the ones in California that maybe you can get 1 million or 2 acres out of. The one in Australia was 44 million acres, just for context. We had NCAR in the news with the NCAR fire. This is obviously snow on the ground, and another event where you had lots of wind coming down at the same time as very dry conditions from the preceding drought. And then a rather unfortunate headline in the paper in the Boulder Daily Camera saying NCAR believed to be human caused. And no suspects have been identified, but I would point you to that guy on the upper right, Walter Orr Roberts. He might be able to identify some, but obviously, there's a climate signal here and what we're seeing in wildfire. And then just this year, this is from last week, we had these fires in Alberta, and we have this video that'll play, kind of shows the smoke coming down from Canada into Wyoming. And it's a rather short video, unfortunately. But the point is clear that we had, in May, fires 1,000 miles north of us that were widespread due to temperatures in the 90s. And that smoke gets advected, and you wind up with a mesoscale-sized plume of, I think, over 1 million acres burned in Alberta as well of smoke. And so the question is, can that have any sort of a climate impact? So like I said, this is kind of to be expected. This is symptomatic of what's going on in the U.S. So this is from the National Climate Assessment. With wildfire, it's very complicated. You have all these different factors that can influence wildfire. You have human intervention, both igniting and suppressing wildfire. You can have human management of forest systems, which makes them more or less likely to burn. So you have all these different effects. It's very hard to capture this in the model. It's part of the challenge of actually having a land model give you the emissions. But I think it's one that we need to face. And you can see this increase here. The climate change component is in the orange, and in the yellowish color is the wildfire change without climate change due to some of the forest management that occurred decades ago. But the interesting thing here is, of course, this is what we expect with climate change, but in our model projections, we actually have decreases in biomass emissions, which contradicts IPCC from the get-go, but it shows that we maybe can do better than that. And it's done under the presumption that it doesn't really matter that much for the climate that you get out, that the direct clear sky effects aren't that large. We know that to be the case. But is that the case generally? And I think we're starting to learn more and more as the climate models particularly become more able to do aerosol cloud interactions, which are key. So I think that's a big part of why CSM2 is the right tool for looking at this. What's happened in the National Climate Assessment Report is symptomatic of what's going on globally. You see pervasive warming and reductions in relative humidity across land areas. There are some exceptions, and you can have exceptions where you have rainfall either overwhelm that relative humidity signal, or you could have irrigation even, or some localized spots. But by and large, these are trends that are happening globally, and we should expect them to continue. They are a manifestation of this land-sea contrast in warming that occurs under climate change. And they're in direct opposition to what, the bulk of aerosol science has been done on sulfate aerosols. A lot of effort on those, but in fact, sulfate aerosols over the coming decades are going to reduce in importance. They're not going to have the strong climate effects that they've had over the past decades. And so you have to think about what's happening with fire emissions in the context of what's happening with sulfate emissions. And in fact, these at some point may become the dominant story from an aerosol point of view. So why do I think we're not giving this topic adequate considerations? So in seasonal climate predictions, none of them have interactive wildfire in their land components. Some of them assimilate aerosol emissions from MODIS, but by and large, none of them have any sort of an interactive fire scheme in the land model, and that's important because maybe fire itself is part of the predictable component of seasonal climate. We don't really know, and what the situations might be. I'll show a situation that I think does illustrate that. In Hindcast and CMIP6, that's the top right panel here, we in 1997 began to have satellite estimates of emissions, and that's what you see on the right, highly variable emissions. And that was just kind of appended onto the climatology, these decadal, smoothly varying decadal climatologies that you get from other sources of information. So we don't have a satellite at that point. We use other records to generate fire emissions estimates. But that was deemed a viable external forcing of the climate system to look at climate change with, which certainly in CSM2 it was not. And actually many other CMIP models, as I'll show you. Bottom right, these are the future emissions in CMIP6. So you can see under different scenarios, you reach the end of the historical record. That's that little peak right there. And then you might go up a bit more, but eventually you start coming down. And that's a signal from deforestation. It's not a climate signal. So we're not estimating the fire weather changes into the future and therefore the fire changes. Instead, we're losing forest, and so you're losing forest fire, which obviously is incomplete. So in most of this work, I'll be using CESM2. Everyone here knows it fairly well, but these runs are fully coupled. The SMILE runs I'll show are initialized. So there's one ocean initial state. Other runs are actually not initialized. I'm using the 1 degree default configuration of CSM2. And this is important because it has this unified turbulence and cloud scheme. So the clouds are improved significantly over the earlier version of the model, which is important, especially with the vertical distribution of clouds, because I'll argue as that vertical distribution of clouds overlaps with the vertical distribution of aerosols is when you get your effect. So if those are distinct in the vertical, due to biases perhaps, you won't get interaction of the aerosols in the clouds, obviously. So that's an important factor. They also use MAM4 and the Morrison-Gettleman 2 microphysics. And so they have both this aerosol model that can represent aerosol aging and changes in the size distribution, and they have the aerosol cloud interactions, so the Toomey effect and the Albrecht effect. And so those are, I'll argue, also are fundamental. Where we can, we use fire emissions estimated from GFED during this 1997 and later period. And then for other states where we're kind of assessing the effects of those emissions, we're going to use the background climatologies from the SSPs. So this climate response to the 2019-2020 bushfire season, I like this TV broadcast picture on the left. It gives you a sense of scale. That's 1,800 miles from top to bottom. And it's not like the whole country was on fire, and it was really the north part that began, where the fires began, and then generally progressed southward as the fire season went on. But the fire season ended up lasting more than twice as long as usual. And those fires did migrate southward to the point where you can see on the upper right at the end of 2019. That's a satellite picture showing the individual hotspots of the fires and then the smoke kind of coming off the Southern Ocean. And so that gives you an initial indication, at least, that the smoke is not staying locally. There's been a lot of work on the impact of fires on local weather, but relatively little on the impact of fires on the global climate. And clearly, those are going to be transported by the winds. Actually, 1974, 75 had a greater burned area. We don't know what the emissions were from those fires. Something like 60 million acres, I believe, in that season. So huge fire signal. And that season ends up being very important for a reason that I'll come back to towards the end of the talk. Some of the research is still ongoing. But suffice it to say, these things can have a global effect. This is a reanalysis from NASA that's used for their field campaigns, and it's assimilating different types of aerosols. You can see the different colors correspond to different aerosols. This is during 2019, 2020. So look at Australia now. We're heading into late October. We have fires in different parts of Australia. That smoke is being advected to the east. As these kick up, you start to get a sense that those aerosols can go all the way around the planet, and in fact, you'll see that a little later in December. There'll be a big plume that comes off. But two main points here is you get these obviously huge injections of aerosols into the atmosphere. There's a seasonality, a seasonal timescale associated with it, not because the aerosols stay in the atmosphere for a year, but because the fires are continually pumping more aerosols into the atmosphere, and enough so that it completely circumnavigates the globe and comes back around over Western Australia. So this is kind of the context for these fires. You also get a sense for all this variability in the system, right? So smoke, it's easy to say where the smoke is coming from, where it's going to, but what are the climate effects? And you can't just look at a map like this and get any sense of the climate effects, and that's where we have to use CESM. So for this SMILE analysis, we're using, this began as an attempt to actually look at the climate response to COVID emissions reductions. We have 50 members that included the COVID emissions reductions, and we had 50 members that included the emissions reductions plus the Australian fires. So differencing those two ensembles gave us an estimate of the force response due to the fires. They have these diverse initial states. It's a fairly noisy ensemble as a result of that. But this is our approach initially for at least looking at the climate response to the fires in the context of this project that was already ongoing. A few of us were very skeptical that the COVID emissions reductions would lead to much of anything. And we thought, well, this might be the interesting thing to look at, actually. What we found out, and this is on the top here now, we're looking at aerosol burdens, a Havmöller of 2019 through 2024. And zonal average, right? So the emissions reductions due to industries in the northern hemisphere being shut down or at least reduced. You can see in the blue there, you see it in the black carbon burdens, you see it in the sulfate burdens. The Australian fires you see in the southern hemisphere. So that's the increase in the black carbon burdens associated with the fires. So some large increases, didn't last as long as the COVID pulse did, but very strong sort of punch to the system. If you look at the radiation fields are down below. You have stippling where you've actually been able to identify a signal that rises above noise in this ensemble. The COVID emissions reductions, in aerosols you can see the signal, but really in the radiation you didn't see much of anything, either the clear sky or the net flux at the top of the atmosphere. So there seems to be some suggestion of a warming due to reductions in aerosols, but it's very weak. It's not really rising above noise, as opposed to what we see in the Australian fire region. We get this robust sort of cooling of the system. Those blue colors are cooling. The all sky extends all the way from the bottom of the plot to the equator, actually broader than you get in the clear sky. And so that suggests that something's going on with the cloud field, and in fact, something was. If you break this signal down now, we're looking from the equator to 30 south. On the top right, in the clear sky shortwave, you see maybe a tenth or 2/10 of a watt per meter squared of cooling at top of atmosphere. You look at the bottom plot, that's the all sky. You have an order of magnitude larger perturbation to the system. So you're near 3 watts per meter squared. And for those of us that study volcanic eruptions, that starts to look very much like a volcanic eruption. More so than any southern hemispherical volcanic eruptions that happened since 1850. There's not much land there. Eruptions tend not to be that influential on a climate perspective. This ends up being much more like an eruption, ironically, than a volcanic eruption. And you think about climate change, and climate change making these events stronger and bigger. And that's going to be your main sort of like punch to the southern hemisphere in the coming decades, probably. So what's going on here? How do we get this increase in shortwave radiation? Bottom left shows a plot of the cloud albedo. So that's the cloudy sky albedo driven by the Australian wildfires. And so everywhere it's stippled is significant. It rises above the noise. And we do get this cooling that's fairly pervasive around the southern hemisphere. One thing to note for now, and we'll come back to it, is you can see that each basin actually has a fairly clear signal. And there's a lot going on here in the response. There's even opposite sign responses around Antarctica and some stuff that goes on across the equator. this is a very noisy ensemble. Like I said, it was not initialized. So you have various ocean states. It's very hard to kind of knock down your signal to noise ratio. But one thing we saw, and we didn't have a whole lot of confidence in making much of in this paper, was the fact that we had a La Nina response the year after. We know that southern hemisphere eruptions give you a La Nina response, and so this seemed very interesting, that this could be a realistic response. But we wanted to knock down the noise, and we wanted to understand, the mechanisms that are connecting the fires to La Nina. I mean, no paper has ever shown that you could actually generate a La Nina event with a wildfire. So this all seemed very speculative, and we weren't sure what to make of it. But let me take a break now and take you back to where we were in June of 2020. Various facts started to line up that made us think something was going on that actually might have connected these things in nature. So June of 2020, NOAA issues its ENSO forecast, neutral conditions in June of 2020. And this is right on the cusp of a record 3-year La Nina. So very poorly forecast. Also did not follow an El Nino event. When you get these long La Nina events, typically they follow a strong El Nino preceding them. So we didn't get the typical Rossby wave hitting the western boundary and driving a Kelvin wave across the tropics. Something very different. This downwelling in the eastern Pacific just kind of showed up. So where did it come from, and why did this event look so different? Why was it so poorly forecast? Remember, this is after the spring persistence barrier, and you'd expect to do better in an ENSO forecast than this at this time of year. And just to underscore how unique this event was, this is Michael McFadden talking about this event in its 3rd year, and making the point that we were setting records for cold SSTs in the Central Pacific Ocean in 2022. Even with climate change on top of the overall warming pattern, it was breaking records since 1950. So very strong event, wasn't well forecast. And so we wanted to know what connected the fires to the La Nina event. And this plot on the left, we're going to use the SMILE ensemble. So this is one ocean initial state. We're going to try to knock down the noise as much as possible. And you can see here some of the sense of the benefit of going to so the range here of the ensemble, for example, this is in the initialized ensemble compared to the uninitialized ensemble, is actually quite much less for at least a year into the interaction. So we know that we're going to get, we expect we get an ensemble mean La Nina out here, and we want to be able to knock down that noise as much as possible. So we're using 30 members of the SMILE ensemble, and we are differencing one ensemble that has the Australian wildfires in it versus one that does not. And otherwise, they're identical. They're just using the SSP 245 biomass, including regions outside of Australia. So the one factor that differences these ensembles is the Australian wildfire emissions. So how realistically are we getting the emissions? As it turns out, not that well, actually. We're underestimating the emissions. And so this red line up here is the emissions estimate from MODIS. And this is our ensemble here. This black line is the ensemble mean, and of course you have lots of variability about the mean. But our initial sense, at least, is that our simulation with CSM2 may be a bit conservative because we are under-predicting the anomalies in the aerosols quite a bit. This is somewhat consistent with a paper by Tilms et al. In 2019. They cited biases in oxidative chemistry as being responsible for some of the underestimates in MAM4. But relative to other models, actually, they tend to do better. It's an improvement, but we're not all the way there yet. And particularly with fire events like this, where we had all these pyrocumulus events off of southeastern Australia, the lack of a plume model in CSM is a problem. So we're not getting that vertical injection of aerosols into the upper troposphere as well as maybe we should. We just are letting these aerosols self-loft, so when the sunlight hits them and they become buoyant, they do move up through the atmosphere, but there's nothing like the explosive nature of the fires and the heat that's generated by the fires to get them to the upper troposphere. So that may be one reason why, and then of course, most climate models have excessive precipitation, at least in the global mean, and so maybe we're raining out some prematurely. But that said, this is what the fire pulse looks like on the top left here in the ensemble mean. And the typical progression of fire is in the gray line down there. So not only are we, a factor of 4 higher than the typical annual peak, but we are also lasting a lot longer and extending this into late 2019. which typically wouldn't happen. The MODIS was suggesting that actually it should probably go a few months further into 2020. So we're not doing too bad. You get a sense of the spatial distribution in the map on the top right. That's roughly in agreement with what we saw from the reanalysis from NASA. And then you get this hemispheric imbalance. So that 3 watts per meter square that the fires are increasing your cloud albedo by is giving you this increased hemispheric albedo. And that's important because that's basically the signature of a volcanic eruption that drives the shift in the ITCZ. So you get this hemispheric imbalance, and that causes things to shift, and then gives you an El Nino or La Nina, depending on which way you change that. So these are all kind of the large-scale responses that we're expecting. The interesting thing now is that we have a totally new ensemble, and we are getting still La Nina-like patterns, both the year after and 2 years later. We only ran these for 2 years. We weren't thinking we were going to get a 3-year La Nina. And so that was, in retrospect, something we wish we did differently, and we have now run a 5-year ensemble, and it gets the 2-year La Nina very nicely and a rapid rebound to El Nino conditions, which is interesting. We're still looking at that. I'll show you a map at the end of this. So we get this La Nina-like difference. If you look at the progression of anomalies in the NIA 3.4 region, they both ensembles, the red and the black, cool initially. And so the initial conditions are predisposed to a cooling of the system. That's not the fires. But then those lines begin to diverge. And you can see the divergence of those lines over time, such that by the time of winter 2021, Northern Hemisphere winter 2021, you get a La Nina event, or you increase the chances for a La Nina event considerably. And that cooling still is growing through the end of our simulations, through 2022 there. And so what are the mechanisms that connect these two things? Generally speaking, it has to do with increasing albedo, but in certain key regions. As these aerosols go across the Pacific Ocean, you can see this red hatched area on the right, and that's the region where these time series correspond to. And so the smoke enters that region, brightens the cloud field. The blue line that you see is the SST inverted. So leading a cooling of the local SST is this increase in cloud albedo, this reduction of shortwave radiation that's reaching the surface. And that's what the map shows on the top. That shows the reduction in shortwave radiation that actually reaches the surface. And we're about 20 watts per meter squared, 20 to 30 watts per meter squared over a large area of the southeastern South Pacific. So significant cooling of the ocean there. And we think this is key to the La Nina response. And then along with this SST reduction, you get a drying of the boundary layer, you get a cooling of the boundary layer. This bottom right here just shows the SST response in that red hatched area. The response of the ITCZ to this cooling is what's key. So that region we just looked at is directly upstream from the deep tropics. You can see the low-level wind field would take any sort of boundary layer moist static energy anomaly and advect that into the deep tropics. And what we see in the time series is now an average over that red area. And the moist static energy decreases roughly on the advective time scale from the area in the southeast South Pacific, and it has roughly the same order of magnitude. So you're seeing this response in the boundary layer off the equator, and that generally gets advected onto the equator. And of course, deep convection doesn't like reductions in moist static energy. So the ITCZ, we're saying, is moving north in response to this kind of cold, dry air coming off over the equatorial Pacific. When that happens, the easterly winds pick up right on the equator, and of course that predisposes the system to Ekman upwelling and feedbacks associated with La Ninas to kick in. And so you can see the reduction of the moist static energy occurring in early 2020, the specific humidity, the boundary layer being a key part of that, the precip responding right at the same time as the ITCZ moves northward. And then I've extended the scale on the right, but the interesting thing is that this cooling lasts to the end of our simulations all the way up to 2022. And so that was quite unexpected, and it's a sustained event. So is CESM2 doing anything reasonable here? Turns out that a lot of the early marine cloud brightening work looked at brightening clouds right in this area. This is with the HADGEM model on the top, on the left here from the UK Met Group, and then also the GFDL model on the right. And both of these marine cloud brightening studies point to this region as being particularly strong in its ability to reflect shortwave radiation when you see the cloud field, but also it has an ENSO response. And in fact, if you look at the key point on the study on the right, that they find that if you brighten the clouds in this area, you actually induce a La Nina-like response. Now, this was with a rather simple model. It's a slab model. They were just basically looking at the ITCZ. It doesn't really capture any of the coupled feedbacks. But this is a new study that we're working on where we're using fully coupled CESM to do marine cloud brightenings by a graduate student at UCSD and also Jack Chen and Nan. And what we're showing here is that if you take that similar area in the Eastern Pacific and you just alter the cloud drop number concentration in a way that's analogous to what we saw in the fires, in fact, you get a fairly strong La Nina. This is based on one member, so early result, but very, very similar climate response to what we saw during the fires. And so I mentioned before all that complexity around the Southern Hemisphere and the climate response. This suggests that maybe our simple interpretation of this region as being important might be right. So we'll see. But obviously, we want to do this with more models and get a full ensemble done. But the initial results are promising. Okay, so in summary, the Australian wildfires drove these increases in biomass burdens and cloud condensation nuclei across the Southern Hemisphere. It had these aerosol and direct effects that brightened clouds and drove a very strong radiative response on the large scale that looked like a volcanic eruption. This reduced absorbed solar radiation that cooled the surface to dry the boundary layer, and then that was advected into the deep tropics, where it caused the ITCZ to move northward, easterly winds to span the equator, and Ekman upwelling and La Nina feedbacks to kick in. And that, at least from our study, we can say that we get a sustained 2-year cooling from that. We really can't comment on the 3rd year, but certainly it seems odd that you have this 3-year La Nina in nature, and we're suggesting that this could be at least a contributor to it. Maybe it doesn't cause La Nina. We're getting a half a degree of cooling, maybe a bit more, and there's a lot of uncertainty in the processes that link these things. So I'm going to move on to topic 2, and this is related in some ways, but basically I'm going to be looking at the CMIP6 biomass emissions response. This is that record I showed earlier of biomass emissions from CMIP6. You have the large variability in the satellite era and climatology beforehand. And what we've done is we've taken out that variability in one ensemble, left it in the other ensemble in the red, and looked at what the force response was to the variability in the biomass emissions. We're keeping everything else identical, same annual cycle, same mean value, only the variability has decreased. And so it turns out we get a climate response in CSM2 from this. The thing that we were concerned about early on was the fact that we saw so much more warming in CSM2, red line here, in the default CMIP6 simulations versus CSM1, which is the blue line that's under this black line here. You see even more prominently that difference in the northern hemisphere. And this is something that lots of us saw during development of the model, and it struck us as really strange. One way to interpret this is, well, we know the climate sensitivity of the model is quite high, and maybe we're just seeing the model sensitivity kick in. But there's reason to doubt that interpretation. And if you look at, as these things go into the SSP portion of the ensemble, you can see this leveling off of temperature. And certainly you wouldn't expect that to be the case if this is ECS that's causing these differences. So when you smooth the forcing, you get an evolution of temperature that's almost identical to CESM1. And very similar to observations as well. So what can be interpreted and what was interpreted by many papers is actually a model bias. It's not a model bias, it's a forcing bias. And there's an error in the forcing that gives you this spurious warming at the end of the historical record. And this goes into the mechanisms a bit, but it's a similar story. There's some nonlinearities at play here that I'll touch on in a second. But generally speaking, you're warming up the northern hemisphere in part because of feedbacks between sea ice and the radiative forcing of the emissions. But you're basically thinning the cloud field, allowing more shortwave radiation to come in. The low cloud amount goes down. And interestingly, the biggest reductions are at low latitudes, around 20 degrees north. And that's also true of the radiation. So these things don't have to be co-located. And as the anomalies in smoke get advected, you see a downstream response in the clouds. And certainly this suggests that subtropical stratoQ deck is uniquely sensitive to these anomalies in aerosols. So the effects of this didn't stay in the northern hemisphere, and you can see the warming response in the top right, and you can see this kind of bridge going into the southern hemisphere. And the ITCC shifts in response to this too. So if you warm up the northern hemisphere, you shift the ITCC northward, and then it tries to equilibrate the hemisphere by driving dry static energy. Look at the top, you can almost see these, this progression of advection into the southern hemisphere. You get more warming aloft than you do at the surface, and that's the system trying to equilibrate to this hemispheric imbalance. This had a lot of effects. Patricia wrote a really nice paper on sea ice, and in fact, Patricia was looking at this parallel track as we were at the same time, and it wasn't until we connected later on that we realized that we both kind of had found the same stuff. But really nice paper looking at the effects on sea ice, and so you have the black emissions or CMIP6, smooth emissions in green. If you look at temperature on the top right here, you see this warming during the raw CMIP6 emissions scenario, and the smooth biomass eliminate that. Well, you see the same thing in sea ice extent, and that's shown down below. You get this rapid reduction in sea ice, and then it actually recovers and maybe increases even for a decade afterward. So these strong ties that you'd expect between temperature, radiation, and cryospheric feedbacks. It's an interesting question. When you look at observations, it has a similar sort of decadal variability. And so I think it remains somewhat of an open question as to whether the signal in the observations is forced or not, but perhaps there's some interesting science to be done on that. We did a study that looked at the troposphere and this disagreement between the satellite estimates of tropospheric warming and CESM2. And so the warming of CESM2 is much greater than is in the satellite record. And of course, the people sometimes view that as a expression of excessive climate sensitivity, which may exist, but there are other ways of getting at that. But certainly this is not evidence for that. The Taylor diagram, by the way, for CSM is very curved, and so you wouldn't even expect to see that warming. The TCR isn't that different than observed, so you wouldn't expect to see that warming until later on in the record anyway. It wouldn't be in the historical record. But suffice it to say that with two effects, the pattern of observed warming and also this effect with emissions, you're able to largely reconcile CSM2 with the satellite record of tropospheric temperatures. And so that's what Stephen Pochedley did, leading this study in 2022 and published in PNAS. We have a study in review right now, in revision, that looks at how long do these effects last, what are their effects on the ocean, and you get this lasting warming. If you look at the red line on the top right here, so that initial heating pulse that you get because of the biomass emissions, that stays in the system. That doesn't get radiated back to space. And so, in fact, all the way out to 2100, the system's taken up this additional heat and stores it. It gives you this relative increase in sea level, let's see if I can, here, which sticks around for quite a while. And then also a weakening in AMOC. So this is the weakening of AMOC through here, which sticks around for maybe another decade or so. And then this is the heating pulse that you get during the biomass emissions era that gets mixed downward in the ocean over time. And all the way out to 2060, 2070, you have this identifiable warming in the ocean due to the biomass emissions that happened during the historical era. So it's pretty long-term memory in the system. The basic nonlinearities that are relevant here are summarized in this plot. This is also from a different paper that's in review at the moment. It's in revision at Nature, Climate, and Atmosphere. And the question is, why do these identical emissions drive such a different climate response? The average is the same, so something must be nonlinear. And there are multiple nonlinearities. There's three here, and then the bottom right is kind of a summary of the three. But you have a nonlinearity between the emissions and the CCN. You have a nonlinearity between the CCN and the cloud droplet concentration. Then you also have a nonlinearity between the cloud droplet concentration and the shortwave flux. And so in total, those give you the curve on the bottom right. And in essence, when you include this large variability, which itself is really skewed, it's not a normal distribution, you end up spending a little time way out on the right of the bottom graph and a lot of time on the steep part of the curve to the left. So you're getting more bang for your buck on the left in terms of shortwave response for a given biomass emissions anomaly. And that's effectively what's happening here is you have many years of below normal emissions and then a few years of very high emissions. And the low emission years win out in the end. So that's why you're warming up the system. I'm going to go through this rather quick because I think we're pretty far along. But suffice it to say that this is not only in CSM2. We see this effect in E3SM. Same idea. You brighten the clouds, you thin the cloud field with variable emissions, and you warm up the system. So the temperature response is that top right in the colored bars, and then CSM2 is in the dashed line. So CSM2 is slightly more sensitive than E3SM2, but they're both showing the sensitivity. Teasing out which model is right is going to be a lot of work, and certainly important work to do too, because these interactions occur across timescales and are relevant to wildfires in the future, but non-trivial for sure. HADGEM, the UK ESM model, and the HADGEM 3 model exhibit the same sensitivity. These are runs that were done by the UK Met, and what they show again is this sensitivity of temperature of about 1/2 degree in the northern hemisphere. Here we only have 5 members, so we can't nail it down quite as well, but you can see the smooth biomass are giving us less warming through here, and more reflective solar radiation, less absorbed, consistent with what we see in CSM2. So this is not just a CSM2 problem. This is something that exists. We've shown 3 models, but we suspect actually much more than that. And we've also seen that some models aren't sensitive at all. The GISS E2 model is not. The GISS E3 might be. The GISS E2 doesn't have the Albrecht effect. And so these kind of things are involved in why you see these intermodal dependencies. Also, the individual sensitivities in that nonlinear curve are really key. So to bring this back to how we started and looking at these areas of energy budget and why it matters, this is meant to kind of put into context the role of wildfire. Almost all of the research on wildfire has these arrows going the other way. ENSO influences the spatial pattern of wildfire. Earth's energy imbalance and warming can influence wildfire and climate change. But in fact, these arrows also go outward. And we think that wildfire is kind of underappreciated, but central component of all of these themes. Some of the science questions are listed there. But paramount really are, what is the role with ENSO and what's the role as a climate feedback? And these are 2 things that I think we can start to look at in the coming decades. Here's the ENSO question. We all in grad school learned that diagram on the right there. You have convection interacting with the ocean, and where's the land surface? Where's wildfire in that? And it turns out that Indonesia is some of the biggest, most carbon-intensive wildfires to occur at any point, part of the planet, and usually occurs during El Nino. And so what is the role as you get these huge fires off of Indonesia and the Amazon? What is the role in ENSO? How does it modify ENSO? I'm not going to spend too much time on this, but that's the progression of wildfire around the tropics. That's right before El Nino at the top, these flare-up of emissions over Indonesia. A year later, you actually have this massive suppression of emissions, and in fact, they've moved over to the Amazon. And then 2 years later, if you go into a multiple-year La Nina, you actually have suppressed conditions throughout the tropics and the extratropics. So how do these things affect ENSO? What are their climate signatures, and do you have to actually represent this if you want to get the energy flows associated with El Nino and La Nina correct? So we're looking at that. This is the 73-74 event that I had mentioned earlier. So we're going back into the record and looking at how might wildfires have influenced past ENSO forecasts. And it turns out there's this canonical event that happened in 75-76 of Wertke's first ever El Nino forecast. And so here he is in 75. He's trying to predict forward what's going to happen in the coming year. Predicts El Nino, fails miserably. Ends up being a multiple-year La Nina, right? So in this paper by Mike McFadden and co-authors, they actually take all the modern forecasting systems and say, well, why did Wertke get it wrong? They simulate the same event. They all get it wrong. They all want to go El Nino when in fact it ended up being La Nina. What gives? Well, we think that wildfires maybe played a role. The largest bushfire season ever to occur in Australia was 74-75, during the exact same time of year as we had in 2019-2020. So what are the connections here between wildfire and this forecast? And so one of our intentions now, we're in the middle of generating the emissions, which are difficult because you're before the satellite era. We have some knowledge of what burned over Australia, but roughly 15% of the continent burned. So huge, so 290 million acres. It's probably less emissions intensive than what we saw in the eastern part of the country because there's not so much forest as grasslands. There are some forests in there, but we're going to make an effort to kind of regenerate these emissions estimates for 74, 75. It turns out that SMILE also misses this year of La Nina. It forecasts an El Nino. So we're going to insert the wildfire emissions and see what happens. So we don't know yet. And then lastly, this is the 5-year simulation that we now have where we can start to address these questions of what happens later on. We get the first 2-year La Nina. It's a completely independent ensemble, which is encouraging. So now we have 3 ensembles, right? 1 uninitialized, 2 that are initialized. All of them give you year 2, year 3 La Nina events. So this seems to be a fairly robust response. And then you get this rapid transition to El Nino in year 4. That ends up being a little bit earlier than what we're seeing in nature. We're going into a strong El Nino now, but maybe the weakness of the aerosol distribution is part of what's going on, but this is, anyway, work that's in progress. And then lastly, what's the role of wildfire as a climate feedback if we realistically extend these fire emissions into the 21st century? How is that going to affect the climate sensitivity of the model? Is that going to cause things to warm up? We don't even know the sign of the response. There are different ways that you can argue it. A lot of it relates to the variability. Both the variability and the mean are likely to change into the future, right? So what is the sign of the climate feedback? No idea. So this is definitely work that CGD can do. We're already doing some of it. We're working with a group in Korea. This is control. We're just at the point now where we have a control simulation that gets the burned area about right. So now we're actually getting emissions from the land model into the atmosphere. And we're trying to get a stable climate, something that looks kind of like the real world. And that's where we are with this run. But ultimately, we want to create ensembles that go through the historical era and also into the future that we can use to quantify the effects of wildfire on the climate feedback and the future trajectory of the climate system. So with that, I think I'll put up my conclusion slide. We're probably a little bit late in things. I'll leave this up. It's basically a reiteration of what I already said, and I'll take any questions.
Thanks, John. So questions?
Thanks. I was just a bit confused about SMILE and the 1974 event. Don't we prescribe the biomass burning emissions in SMILE? So it's just we didn't know properly what happened? Or?
Yeah, so SMILE by default is using the CMIP6 historical emissions, which they're in that area of climatology, right? So they're not actually using a realistic pulse of aerosol emissions from the continent.
Okay.
Right, so the idea would be to come up with, as best we can, estimate what those emissions might have been, and then run a companion ensemble with those new emissions. And we expect, based on what we already know, that that's going to become more La Nina-like. To the extent that we actually get a forecast that pans out, we don't know. But that's the thinking behind that work.
But then in the GFED era, the CMIP6 emissions do have the fires that occurred, or
not in 2019, 2020, right? So
no, but in general, in SMILE, for that whole couple of decades, we're giving the model emissions that happen. No.
So GFED, Steve can speak to this more than I can, but it uses.
Okay.
Yeah.
But if we did give it CMIP6 emissions, it would have fires that are maybe not predictable.
It depends for what era, right? So anything after 2015 is going to be an SSP.
Yeah.
So you're not going to have it in that. But yeah, from 1997 to, and in fact, I mean, it's a great point that you raise, is that you can actually use the CSM2 large ensemble. It has a set of simulations where you have smooth emissions and a set that have the CMIP6 variability. And you can see ENSO responses in the CSM2 large ensemble directly. No one's actually done research on that, so anyone looking for a project.
But so other prediction systems that maybe use the CMIP6 emissions over that period will be imposing a forcing that maybe wasn't predictable if you were, to do it in real time.
Which period?
The GFED era.
Yeah.
So they would have maybe really good ENSO skill because they're.
Well, I don't want to oversell it, right? I mean, my perspective on this is that this is going to be a factor that probably becomes important during specialized circumstances, right? I mean, you still have ocean dynamics and waves that are going to drive ENSO unless something else comes along that's really big. In 2019, 2020, that was a really big hammer. But by and large, you're not going to get that kind of climate forcing during most years. I mean, I think just certain years you might see this.
An online question?
Yeah. So, John, Cindy from online asked the question: the Australian fires caused cooling for more than 2 years because of the albedo changes and the La Nina effects. But what about longer term scales, like so from increases in black carbon on snow or greenhouse gases? Is there any way of being able to work out the relative impacts in terms of greenhouse gases versus aerosols?
It's a tough question. So we don't actually include the elevated greenhouse gas emissions from the fires. So we're just using SSP and historical concentrations. We don't, I mean, really, to have confidence in CESM beyond kind of like sign of change is difficult because there are so many links to the chain. So I wouldn't want to make any speculative statement about the relative importance of cooling versus warming. So I just don't think the science is there yet.
Another question? I knew Peter had one. I'll come back and then I'll go to, okay.
So the fact that when you smooth the emissions, you get a better representation of the increase of temperature over the 20th century. So are you implying from that those observations of the emissions are incorrect?
No, so there are two different things, right? One is the ensemble mean warming, and one is, and this touches on a philosophical issue as well, is that variability that you saw has to be consistent with the meteorology that drove those fires. When you impose that variability on free-running uninitialized simulations, there's no guarantee, in fact, you know that most of the simulations are going to be incompatible with the emissions, right? So the effects that you may get radiatively, you may have a cold, wet winter during summer during this strong fire pulse, right? So completely unrealistic. So what I am saying is that even if those fires drove a certain amount of warming in nature, it's one ensemble member. And if you want to get the forced response over the 20th century, you need an ensemble that's realistic. And any ensemble that's using CMIP6 emissions is not going to be realistic.
So what do you conclude is the best way to represent the fire emissions in the scenarios?
It's such a hard problem, yeah, for sure. And I mean, I didn't touch on all the issues that make that difficult. We don't actually know whether how fire, and there are other people in this room that could address this better than I can, but we don't know what the trends of the 20th century is of aerosol burdens in the atmosphere. And I've heard it mentioned by some experts that in fact the fire emissions that we have now are about on par with what we would expect in an equilibrium climate because we have capped them so much with suppression efforts, and they've reached a point where they're kind of coming up on their own, even with our suppression efforts, to be about even, right? And so currently we have no way of getting the mean emissions, not to mention the variability, which is so critical to the climate response. It's extremely difficult. I don't know of anyone that, a few groups that are actually even working on it, but Sam is here. I saw him. Yeah, I don't know if you want to comment on it or yeah, anyone who feels like they could. But I don't, anyway, I'm not the expert in the room on that, and it's extremely difficult.
Do you want the microphone?
Okay.
Okay.
Yeah, but those are some of the issues, right? Is that you don't actually know what the past emissions were, and it's not as simple as the warming trend or even the fire weather trend over the U.S. because there's been all these efforts to suppress fires at the same time that climate change has been going on, and so the plot that I showed began in 1980. I think for this very reason, is it didn't want to make a commentary about the change in fire amounts before 1980, because doing so, it's tough to disentangle the multiple effects on fire that are going on.
Yeah, we have another question online. Bill asked the question, considering the CSM aerosol burdens were low, and I assume this is against the MODIS aerosol optical depth, would that suggest to be an influence on why the persistent La Nina were underestimated in the SMILE AU fire?
Yeah, it's a possibility. So, and it's something that we can investigate. So we could, like I say, there are multiple links to the chain and uncertainties in each one of them. So it's not obvious to me that our radiative forcing of the event is weak relative to nature, even if the aerosols themselves are underestimated. That said, you could just double your emissions, right, and run the ensemble and see what happens. Do you get a 3-year La Nina as a result? And it speaks to one avenue for how we make progress, and that is that you try to hone your aerosol effects to optimize your prediction skill in SMILE, and then you use them for your climate projections, because you're never going to be able to validate your climate projections, and the uncertainties are very large. So that's one possibility, is that you approach it that way. But it's possible that the low aerosol amounts lead to a too short La Nina, but I'm far from convinced that that's the case necessarily. We could look at that.
A bit simpler than Peter's question about the SSPs and biomass burning, is what biomass burning, I guess, should be used for control simulations. I was wondering if there are any records of the statistics of this. And I mean, based on what you've argued here, that would seem to impose an asymmetry in El Nino. I was wondering if there are any other lines of evidence we can look for to test that hypothesis, either from paleo or something else.
So it can work both ways in terms of El Nino and La Nina, and volcanic eruptions do as well. So Northern Hemisphere eruptions give you an El Nino, Southern Hemisphere give you a La Nina in the year after. And so there have been some very large, 2017 had one of the largest Siberian wildfire seasons in record, and simulating that is definitely of interest. But I don't know if you could back out what the variability would be across the 20th century from any asymmetry. El Nino and La Nina are so noisy, right? And so here we have the benefit of 30 members, 50 members to average out that variability, and we still actually can't say things that precisely. The La Ninas in the new 5-year runs are quite a bit stronger actually than in our initial ensemble and the ensemble mean. There's so much noise that I don't think you have any meaningful constraint on the biomass emissions from the behavior of ENSO over the historical record.
Sorry, I'm not jumping the queue. One of the things that's really interesting is that the Australian fires were preceded by extreme drought, like basically off the record drought, and we can say similar sorts of things for West Coast fires. So these really arid, really hot conditions seem to have a climate change signal to them. Would you comment on that at all, or need to have a fire model that could respond to it?
Well, the thing that comes to me initially is how wrong someone's intuition can be on some of these aspects. The 74-75 bushfire season is due to excessive rain. Right, so the years before, that's the 3-year period from 73 to 76 is one of the wettest 3-year periods in Australian history, right? And so these fires came about because you had 2 years of really strong growth, and then it just became Australia. It was really dry and it was really hot, and all that stuff that grew burned. And so, yeah, some of these things, that's the thing that strikes me, is that a lot of fire behavior can be, at least for a physical scientist, very non-intuitive. So I'm left with that.
But I guess I was really not meaning the 74, 75 fires. I mean the 2019, 2020 fires. They had 3 years of extreme drought, and the forests were ready to burn. And I was wondering if there was a lot of discussion about the climate signature, the climate change signature on those fires.
Yeah, there's no question that there's I've seen studies on that have said that it's almost virtually certain that climate change was a major contributor to that wildfire season. Other seasons may be a bit more uncertain, but yeah, it's almost certain as well. IPCC has, in fact, they have statements regionally about the behavior of fire. There we go. So certain areas, they have high confidence that you're going to see increases in fire, and the changes that we've seen. So if you remember that original plot that I showed up that showed the global change in fire weather, it's roughly consistent with these kind of changes in regimes. So yeah, and especially the Australian wildfire, I don't think there's much doubt at all that was enhanced by wildfire, as by climate change.
Okay, one last question.
Thank you. I'm a visiting student, so forgive me if this question is dumb. I think the logic is bushfire emits AOD and then CCN and then cloud properties and then radiation and then El Nino and La Nina. This is really a chain, and then every step is influencing the next one. And the prediction was like in 2 or 3 years later. So CSM is a nice tool to do this, quantify this influence. But I'm wondering if precipitation itself is contributing to its story here. So how much do the emission from the bushfire is represented in the CEM is one issue. How wet scavenging is presented by the CESM as from the perspective precipitating efficiency is another thing. In other words, the influence might be just cancelled because of more precipitation has been caused in the model. Have you checked the precipitation compared to the observation?
Yeah, so on large scale, the precipitation is about 10% too large in CESM2 compared to observations. Now, there's a debate as to whether the observations are missing some light rain processes or some of the heaviest extremes. But I think there's general consensus that climate models generally overestimate precipitation. But precipitation is definitely involved. It's involved on the front end, like the drought that set up the fires. It's also involved in interaction with aerosols, the scavenging, and that's not just about precipitation amounts, but also the aerosol microphysics that cause the scavenging to happen. So yes, I mean, you're totally right. Precipitation is involved in multiple parts of the chain. It's not clear to me which way CESM is biased. I think the lack of a plume model. So a plume model is a kind of a subcomponent of the model that gets the vertical distribution right due to the effects locally with the fire. I think that's the first and most likely source of bias in CESM.
Okay, so let's thank John and have a nice evening.